On April 18, 1955, newspapers around the world announced the death of a great scientist. They published a photograph of Albert Einstein's desk with an open notebook, in which he had been taking notes and working on a theory that would ultimately define his life's path: the unified field theory. This concept, also known as the theory of everything, represents the quest for a single equation that could unify all the forces of nature, that is, to connect gravity, electromagnetism, strong and weak nuclear interactions. Einstein's aspiration to find this equation was driven by his belief that understanding the fundamental principles governing the universe would allow us, in his own words, to read the mind of God. 6 years prior to this, 2 weeks after his 70th birthday, which he referred to as a sad event, Einstein, in a letter to Maurice Solovin, confessed the following: "You think that I look back on the affair of my whole life with complete satisfaction. Up close, everything looks different. There is not a single concept about which I would be certain that it will remain steadfast. I'm not even sure that I am on the right path at all. Contemporaries see me as a heretic and a reactionary who has, so to speak, outlived himself. All of this, of course, is a matter of fashion and is explained by their lack of understanding, but a feeling of dissatisfaction rises within me." Einstein struggled for decades to overcome the mathematical difficulties of creating a unified field theory. However, he certainly didn't consider his work useless or senseless. On the contrary, in a letter dated December 14, 1946 to Michel Bessot, with whom he shared his deepest thoughts, the scientist called his work fruitful and had faith in the future. Hope also permeates his letter to Michel dated April 15, 1950, although Einstein acknowledges the unimaginable complexity of the task. From here, it follows that the possibility of comparison with anything known from experience is to be expected only in the case when strict solutions of the system of equations are found, in which the known images from experience and their variable impacts reflect. But since this is monstrously difficult, one can understand the skeptical position of contemporary physicists. For now, they have every right to consider my path unproductive. But this will not continue for long. Gradually, they will see that the quasi-empirical method will not unravel the essence of things. What was this skepticism of contemporary physicists about? And how did the author of the theory of relativity and the very formula E equals mc squared, which vividly explains the fundamental relationship between mass and energy, become almost a dissident by the end of his life? Let's figure it out. If in the 1920s physicists looked upon Einstein's effort to create a unified field theory with admiration and hope, by the 1930s, against the backdrop of impressive successes in quantum mechanics and quantum field theory, Einstein's authority had noticeably diminished. None of his attempts to derive specific equations of motion for elementary particles from general scheme were successful. Meanwhile, quantum physics was proving to be astonishingly productive. The year 1932 was especially rich in discoveries. In this year, just 5 years after the final formulation of the Copenhagen interpretation of quantum mechanics, new elementary particles were discovered: the neutral neutron, which along with the proton makes up atomic nuclei, and the positively charged positron, the antiparticle of the electron predicted by Paul Dirac. Here is an interesting historical paradox. The honor of being the discoverer of antiparticles should have belonged to Albert Einstein, but he missed this opportunity, being too engrossed in the search for a unified field theory. 3 years before Dirac, in the fall of 1925, Einstein published a short article titled "Electron and the General Theory of Relativity" in the Dutch journal called Physica. It begins with an unusual phrase for scientific articles. The following remarks are so simple that I do not expect to say anything new in them. From today's understanding of physics, this phrase indicates that the author did not fully grasp the brilliance of what he had done. After all, it was nothing less than the discovery of antimatter. This example vividly demonstrates his total focus and concentration on the theory of everything. Some of Einstein's contemporaries looked at his scientific efforts with pity, while others, allowed themselves mocking jokes. The huge difficulty of the task did not discourage Einstein until the last days of his life. He battled mathematical problems sparing no effort, much like Don Quixote fought windmills. Einstein himself recalled the hero of Cervantes' novel in that letter dated April 15, 1950, one of his last messages to Michel Besso. It's true that under such circumstances you find yourself in the position of Don Quixote, as there is no assurance that there will ever be an opportunity to know whether the theory is true or not. But the longer the struggle for a unified field theory lasted, the more frequently doubts came to mind. In one of the subsequent letters to a friend, they expressed most vividly, 50 years of conscious search have not brought me any closer to the answer to the question, what are light quanta? Today, every passerby thinks that he knows it, but he is mistaken. I am now confident in the possibility of a natural generalization of gravitational equations, but I cannot figure out whether there is anything physically true behind it. Erwin Schrödinger, Werner Heisenberg, Niels Bohr, Paul Dirac, Max Planck, Richard Feynman, Julian Schwinger, Abdus Salam, Steven Weinberg, Sheldon Glashow, Murray Gell-Mann, Stephen Hawking, Roger Penrose, John Archibald Wheeler, David Gilbert, Hermann Weyl, Oscar Klein, Edward Witten, Brian Greene, Juan Maldacena, Michael Green, John Schwartz, Gerard T. Hooft, Carlo Rovelli, Lee Smolin, and Kip Thorne. This list can go on and on and on. All these are names of scientists who worked on the theory of everything. But did it result in anything? Has anyone among them managed to derive the God equation? Today, many leading physicists believe that we have finally approached the solution, and perhaps the main candidate for the role of the theory of everything is called string theory. It posits that the universe is not made of point particles, but of tiny oscillating strings, each node of which corresponds to an elementary particle. Within this theory, if we take a super powerful microscope, we would see that elementary particles such as electrons, quarks, and neutrinos are nothing but oscillations of tiny threads, resembling a stretched rubber band. If we tweak such a rubber band differently enough times, eventually we will get all non-elementary particles of the universe. This implies that all laws of physics without exception can be reduced to the harmonies of such strings. Chemistry is the melodies that can be played on the strings. The universe is a symphony, and the thoughts of God, so eloquently written about by Einstein, are cosmic music resonating in space-time. Nobel laureate in physics David Gross wrote, "String theory is a part of 21st century physics that fell by chance into the 20th century." Here are the words of Kip Thorne. "String theory is an amazing theoretical development that strives to unify all forces of nature into a single coherent picture. It's a bold and beautiful idea, captivating the imagination of physicists around the world. Indeed, the pursuit to find such a strong candidate for the role of the theory of everything like string theory is not merely an academic question. Each time new laws of physics are discovered, the course of civilization and the fate of all humanity are altered. For instance, Newton's laws of motion and gravity laid the foundation for the age of machines and the Industrial Revolution. Michael Faraday and James Clerk Maxwell laid down the foundations of the theory of electricity and magnetism, which enabled us to illuminate cities, create powerful electronic motors and generators, as well as communication means like television and radio. Einstein's formula E = mc² explained where stars derive their energy from and helped harness the energy of the atom. The creators of quantum mechanics, Erwin Schrödinger and Werner Heisenberg, along with other physicists, spearheaded today's high-tech revolution with quantum supercomputers, lasers, the internet, and the gadgets surrounding us. Ultimately, all the wonders of modern technology are the result of discoveries made by scientists studying the fundamental interactions of our world. And currently, science seems to be nearing the creation of a theory that will unite all four forces of nature. But what questions could the theory of everything answer? Roughly the following. What happened before the Big Bang? Why did this explosion occur in the first place? What is the nature of dark matter and dark energy? What lies within a black hole? Are time travels possible? Do wormholes that lead to other universes exist? How many universes are there and what is their nature? Do higher dimensions exist? And how to interpret the double-slit experiment and the quantum superposition of an electron? This video is dedicated to the search for the ultimate theory and some events of one of the most astonishing chapters in the history of physics. We will recall past discoveries that gave rise to the marvels of technology, from the Newtonian revolution and the exploration of electromagnetism, understanding the theory of relativity and quantum mechanics, to the contemporary string theory and some other theories that offer a fresh perspective on the structure of reality. Physicists and mathematicians are in search of one elegant equation that could encompass everything, from the tiniest subatomic particles to the grandest cosmic structures. But love and interest in science can be expressed in simpler and more particular ways too. For example, reading books by Michio Kaku. He's one of the most famous theoretical physicists and also a co-founder of one of the branches of string theory, named string field theory. Creating this video was inspired by his book called The God Equation, The Quest for a Theory of Everything. If you want to deeply satisfy your curiosity and gain structured knowledge, go read or listen to this book. Here is my attempt to tell you a brief history of physics in 15 minutes, in a way that answers the main question: what is the theory of everything? The ancient Greeks were among the first to attempt to bring order to the seemingly chaotic world around them. Philosophers like Aristotle believed that everything could be reduced to a combination of four basic elements: land, air, fire, and water. However, it was challenging to explain the world's complexity with just these four elements. The Greeks proposed two different explanations for this issue. The first explanation came from the philosopher Democritus, who posited that everything is made up of tiny, invisible and indestructible particles called atoms, which translates to indivisible in Greek. Critics argued that direct evidence of their existence was unattainable, as atoms are too small to be observed directly. Nevertheless, Democritus presented persuasive indirect evidence, such as the gradual wear of a gold ring, implying the presence of atoms even if they were invisible. Even today, a significant part of our scientific understanding relies on indirect evidence. We gather information about the sun's composition, the complex structure of DNA, the age of the universe, and much more through indirect measurements, despite never having observed these phenomena directly. This difference between direct and indirect evidence becomes crucial when discussing the proof of a unified field theory. The second approach to understanding the world was proposed by the mathematician Pythagoras. He had an epiphany and decided to apply mathematical description to such an earthly phenomenon as music. Legend has it that he discovered a connection between the sound produced by a lyre string and the vibrations caused by hammer strikes on a metal rod. He realized that both generated musical frequencies within a particular range. This discovery implied that something as aesthetically pleasing as music could be based on the mathematics of vibrations, suggesting that various objects in the world might be governed by the same mathematical principles. In other words, all the diversity of objects around us should adhere to mathematics. In the 17th century, there were scholars who dared to challenge prevailing beliefs and explore the nature of the universe. Johann Kepler, one of the first to use mathematics to understand the movement of planets, served as an imperial advisor to Emperor Rudolf II and avoided persecution due to the inclusion of religious elements in his work. Giordano Bruno, a former monk, was less fortunate. In 1600, he was convicted of heresy and executed. His crime was the speculation that life could exist on planets orbiting other stars. Indeed, what a horrendous crime. Galileo Galilei, often regarded as the father of experimental science, narrowly escaped a similar fate. Faced with the threat of death, he recanted his theories. Nonetheless, he left behind a telescope, an invention that fundamentally changed the scientific world. Through the telescope, one could see that the moon's surface was cratered, that Venus went through phases corresponding to its movement around the Sun, and Jupiter had its moons, all of which were considered heretical ideas. Sadly, Galileo was placed under house arrest and forbidden from receiving visitors. Eventually, he went blind, possibly from gazing at the Sun through his telescope. Galileo died a broken man, but in the year of his death, a child was born in England who continued the work of Galileo and Kepler, ultimately developing a unified theory of celestial mechanics. Isaac Newton is arguably the most influential science in human history. In a world preoccupied with magic and witchcraft, he had the audacity to develop universal laws of celestial mechanics and utilize recently invented mathematical methods known as integral and differential calculus to study natural phenomena. As physicist Steven Weinberg said, with Isaac Newton, the modern dream of final theory truly begins. At some point, Newton's theory was regarded as a theory of everything, capable of describing any motion. It all started when Newton was 23 years old. The University of Cambridge was closed due to the plague. One day in 1666, while strolling through his estate, he saw an apple fall and posed a question to himself that would alter the course of human history. If the apple falls, does the moon fall too? What? In his notebook, he sketched a fateful drawing. If you fire a cannon from the top of a mountain, the cannonball will travel some distance before falling to the ground. However, if you increase the speed of the cannonball, it will travel further, and at sufficient speed, it will go on a trip around the world. Newton concluded that the same law of nature governing the movement of apples and cannonballs, namely gravity, is responsible for the movement of the moon around the Earth. To describe this, Newton introduced the concept of forces. Objects move because they are pulled or pushed by forces that are universal, measurable, and can be mathematically described. Thus, Newton proposed the key concept of unification. In 1682, a significant event occurred that altered the course of history. A brilliant comet appeared in the sky, and everyone from royalty to commoners eagerly discussed the surrounding news. Where did it come from? Where is the comet heading? What does it foretell? Edmund Halley, an astronomer, was particularly intrigued by this comet. He traveled to Cambridge to meet with Isaac Newton. By that time, Newton had already gained fame for his theory of light. By passing a sunbeam through a glass prism, Newton demonstrated that white light separates into all the colors of the rainbow. Additionally, Newton invented a new type of telescope where mirrors were used instead of lenses. Inquiring about the widely discussed comet, Halley was astounded to learn that Newton could prove that comets follow elliptical orbits around the Sun, and even predict their trajectories using his theory of gravity. Moreover, Newton observed comets through his uniquely designed telescope, and their movements precisely matched his predictions. Halley was amazed. He immediately grasped the significance of this scientific breakthrough and offered to cover the costs of printing the work that was destined to become one of the most important scientific publications. Mathematical Principles of Natural Philosophy, or simply Principia. As predicted, Halley's comet appeared over Europe on Christmas Day in 1758, making the reputations of Newton and Halley even stronger after their deaths. Newton's theory of motion and gravity is considered one of humanity's greatest intellectual achievements, as it includes a unifying principle that binds the known laws of motion. Even today, it is Newton's laws that allow NASA engineers to navigate space probes through the expanses of the solar system. Throughout the centuries, numerous confirmations of Newton's laws emerged, significantly impacting both science and society. In the 19th century, astronomers observed a peculiar anomaly in the sky. The position of the planet Uranus significantly deviated from predictions based on Newton's laws. Its orbit was not a perfect ellipse, but slightly distorted. This suggested that either Newton's laws were inapplicable in this case, or there existed another unknown planet influencing the orbit orbit of Uranus with its gravitational pull. The trust in Newton's laws was so strong that physicists, including Urbain Le Verrier, began calculating the presumed position of this mysterious planet. In 1846, astronomers discovered the planet in the predicted location with a deviation of only 1 degree and named it Neptune. Thus, Newton's laws provided the key to understanding the mysteries of planets and comets, laying the foundations of mechanics, allowing us today to build bridges, skyscrapers, engines, jet aircrafts, trains, rockets, and space probes. These are not just dry and dull equations. They are part of our understanding of the structure of reality, leading to an evident consequence: the change in how modern civilization developed. Basically, it created the wealth and prosperity we see around us. Newton's laws, based on unifying the physics of the heavens with the physics of the earth, helped to start the first great technological revolution. It took another 2 centuries for the next major breakthrough to happen, resulting from the exploration of electricity and magnetism. Since ancient times, people knew that magnetism could be used. For example, the compass, invented by the Chinese, sped up the start of the era of geographical exploration. However, electricity terrified people, as it was believed that lightning was a manifestation of the god's wrath. Michael Faraday was the one who laid the foundations of this new field of knowledge. It's said that whenever he attended a party, he was always positively charged. Faraday demonstrated that when a magnet moves inside a wire loop, electricity is generated within the wire. This was a remarkable and key observation, as the connection between electricity and magnetism was previously unknown. It can also be demonstrated that a moving electric field creates a magnetic field. Gradually, Faraday concluded that these phenomena were 2 aspects of the same essence. This simple observation led to the era of electricity, where constructed hydroelectric power stations could illuminate entire cities. Faraday also introduced the concept of a field, one of the most crucial ideas in physics. A field consists of force lines filling space. Magnetic lines surround every magnet, and Earth's magnetic field extends from the North Pole to the South Pole. Even Newton's theory of universal gravitation can be interpreted from the field's perspective. Earth orbits the Sun because it resides within its gravitational field. Faraday's discovery helped explain the origin of Earth's magnetic field. Since the Earth rotates, its internal electric charges also move. This constant motion within the Earth creates its magnetic field. Currently, all known natural interactions in the universe are described precisely by the language of fields, initially introduced by Faraday. However, studying fields required a new area of mathematics, specifically vector calculus, which was used by James Clerk Maxwell. Maxwell was a master of mathematics who made a remarkable breakthrough in physics. He realized that the behavior of electricity and magnetism, as described by Faraday and others, could be generalized and expressed in precise mathematical language. But there was something weird. One law stated that a moving magnetic field could create an electric field, and another law stated the opposite. A moving electric field could create a magnetic field. How so? Maxwell had a brilliant idea. What if a varying electric field creates a magnetic field, which in turn generates another electric field, which then generates another magnetic field, and so on? He guessed that the end result should be a traveling wave, where electric and magnetic fields constantly alternate. Using the methods of vector calculus, Maxwell calculated the speed of this traveling wave and obtained a value of 310,000 km per second. The result astonished him. Within the margin of experimental error, the obtained speed was remarkably close to the speed of light. Then he took another bold step and proclaimed that this was light itself. Light is an electromagnetic wave. Today, Maxwell's equations are the basis of television, lasers, electric motors, generators, and much more. They not only provided us with the ability to have almost instant communication via radio, cell phones, and fiber optic cables, but also unveiled the entire electromagnetic spectrum, in which visible light and radio waves are just 2 ranges. In the 1660s, Newton demonstrated that white light could be separated into all the colors of the rainbow by passing it through a prism. In 1800, William Herschel posed a simple question: what lies beyond the edges of the rainbow with its color range from red to violet? He took the prism which produced a rainbow in his laboratory and placed a thermometer beyond the red color, when no color was visible at all. Unexpectedly, the temperature in this seemingly empty spot began to rise. This meant that besides red, there was another color, invisible to the human eye but still containing energy. It was named infrared light. Now we understand that there is a whole spectrum of electromagnetic radiation, much of which is invisible, as each of its regions has a specific wavelength. This means that the reality we see around us represents just a tiny snippet of the full electromagnetic spectrum, a very small element of a much more expansive universe of electromagnetic shades. Some animals see much more than we do. Bees are capable of perceiving ultraviolet radiation, invisible to us, but important for bees as it helps them find the sun and orient themselves by it, even on a cloudy day. And since flowers evolved their splendid colors to attract the necessary pollinators like bees, this implies that they often look even more appealing when viewed in the ultraviolet range. The mantis shrimp has 12 types of photoreceptors, perceiving a range of wavelengths from 300 to 720 nanometers, meaning it sees in the optical, infrared and ultraviolet ranges of the spectrum, just like a predator. The unification of Newton's and Maxwell's equations provided us with a quite convincing theory of everything, at least everything that was known at that time. At the turn of the 19th and 20th centuries, many scientists declared the end of science. It was a turbulent period when it was believed that everything that could be discovered had already been uncovered. At that time, physicists didn't know that the two pillars of science, Newton's equations and Maxwell's equations, actually contradicted each other, and one of them was destined to fall. A 16-year-old teenager held the answer to this puzzle. This individual was born in 1879, the year of Maxwell's death. As a teenager, Einstein pondered a question destined to change the course of 20th century history. He asked himself, is it possible to outrun a beam of light? Years later, he wrote that this simple question was key to his theory of relativity. Over the next decade, he diligently sought an answer. Unfortunately, many saw him as a failure. Despite his exceptional grades, professors disapproved of his carefree approach to life. Since he was already familiar with most of the material, he often skipped classes, leading to unfavorable evaluations from his professors. His job applications were repeatedly rejected. At one point, to support his wife and child, he even considered selling insurance policies. Hey, imagine opening your door to find Einstein trying to sell you insurance. Unable to find work, he felt like an outcast in his own family. In a letter, he gloomily wrote, "I am just a burden to my family. It would have been better if I had never been born." Eventually, he landed a job as a third-class clerk at patent office in Bern. In the quiet of the patent office, Einstein returned to the question that had haunted him since childhood. It was there he was destined to start a revolution, turning physics and the world upside down. Einstein wondered, what would happen to Maxwell's equations if an object moved at the speed of light? Interestingly, no one had asked this before. Using Maxwell's theory, Einstein calculated the speed of a light beam relative to a moving object, like a train. He expected that the light speed observed by a stationary observer outside would be the sum of the regular speed of light and the speed of the train, because according to Newtonian mechanics, speeds should add up. To Einstein's surprise, he found that the light beam continued to move away at the same speed. This seemed impossible. According to Newton, if you move fast enough, you can catch up to anything. Common sense suggests the same. Yet, Maxwell's equations claimed catching up to light was impossible. This realization was a revelation for Einstein. Only one could be right, either Newton or Maxwell. But why can't light be overtaken? Einstein's epiphany was that since the speed of light is measured using clocks and rulers and is constant no matter how fast you move, space and time must warp to maintain this constancy. This means if you're in a fast-moving spaceship, clocks inside the spaceship run slower than on Earth. The faster you move, the more time slows down. This is a phenomenon described by Einstein's special theory of relativity. Therefore, the answer to what time is it depends on your speed. If the spaceship moves close to the speed of light, and we observe it from Earth through a telescope, everything inside appears to move slowly. Moreover, everything inside seems compressed and becomes heavier than before. However, astronauts inside feel everything is normal. Einstein later said, "I owe more to Maxwell than to anyone else." Today, conducting such an experiment is not difficult. If you put atomic clocks on a plane and compare them with those on Earth, you'll see they run slower, by a tiny fraction, 1/1,000,000th. But if space and time can change, then everything measurable, including matter and energy, must also change. The faster you move, the heavier you become. The source of this extra mass is the energy of motion. For example, if you weighed 70 kilograms, moving at 90% the speed of light would make you weigh 160 kilograms. At 99%, it would be about 500 kilograms. And if you accelerate just a little more, less than 1%, to 99.99%, your mass would be 5 tons. The precise relationship between matter and energy is described by the formula E equals mc squared. This equation also answers one of the oldest scientific questions: why does the sun shine? The answer is simple. The sun shines because the compression of hydrogen nuclei at very high temperatures converts some of their mass into energy. The key to understanding the universe is unification and combining. For the theory of relativity, this is the unification of space and time, as well as matter and energy. But how is this achieved? For poets and artists, beauty is a fleeting aesthetic characteristic that evokes strong emotions and passion. For physicists, beauty lies in symmetry. Equations are considered beautiful when they possess symmetry, meaning that swapping or replacing components leaves the equation unchanged. It just stays the same through this change. Similarly, a snowflake is beautiful because its shape remains unchanged when rotated by 60 degrees. A sphere has even greater symmetry. Rotate it around its center at any angle or direction and it stays the same. Some animals have body parts symmetrically arranged around the central axis, like the radial symmetry of a starfish. Fractal symmetry in nature is seen in Romanesque broccoli, as the same pattern repeats at different scales. Each smaller part of the broccoli represents a mini version of the whole. There are more interesting types of symmetries, like scale symmetry in self-similar objects, such as Sierpinski triangle. It shows scale symmetry where the same shape appears at different scales, but the overall structure remains unchanged. The atomic structure of a crystal lattice demonstrates inversion symmetry, where the arrangement of atoms remains unchanged when inverted through a central point. Why so many examples of symmetry, you might ask? I mention it because it is intuitively and deeply satisfying to us. It is basically a part of us. The human body has bilateral symmetry, meaning it can be divided into two identical halves in a central plane. This plane runs vertically from the head to the feet, splitting the body into left and right sides, which are roughly mirror images of each other. Although the human body is not perfectly symmetrical, many of its features and structures, both external and internal, demonstrate symmetry. External bilateral symmetry includes eyes, ears, arms, and legs. Internally, the human body also shows symmetry in organs like the lungs and kidneys. Physicists find an equation beautiful when its parts and elements can be interchanged without altering the result, that is, when there is symmetry among its components. To any physicist in the first half of the 20th century, it was clear that Newton's theory of universal gravitation and Einstein's theory were incompatible. According to Einstein, if the sun suddenly disappeared, Earth would only feel its absence after 8 minutes. In Newton's famous gravity formula, the speed of light is not included, meaning that gravity spreads instantly, breaking the laws of relativity, and Earth should feel the sun's absence immediately. Einstein spent 10 years describing the nature of light. Then another decade on gravity. the answer to what is gravity came to him when, leaning back in his chair, he almost fell. He realized he felt weightless at the moment of falling. Einstein recalled this as the most joyful idea of his life. Imagine being in an elevator that suddenly breaks and starts falling. You would feel as if gravity doesn't exist, because you on the elevator floor would fall at the same rate. This correlation between acceleration and gravity is called the principle of equivalence. Many think astronauts in space are weightless due to the absence of gravity, but in reality, the ISS and the astronauts are falling towards Earth at the same rate, creating the illusion of no gravity. In other words, acceleration in one frame of reference is identical to gravity in another, explained by the curvature of space. To clarify this, let's look at the solar system. On Earth, we feel gravity as a force pulling us towards the Sun. However, an external observer sees no force. To them, the space around Earth is curved, and this void makes Earth orbit the Sun. It's important to realize that it's not a force pushing the planets, but space curved by mass making planets fall. During high school, I studied in the Lyceum specializing in physics, and one of the brightest memories I have of that time is watching a solar eclipse in all its glory with special equipment. And it made me forever remember the two ways Einstein tested his theory of relativity. The first is gravitational lensing. Simply put, it describes how light rays, being massless, should travel straight. But passing near massive objects, especially black holes, their path bends due to the deformation of the space fabric. Einstein realized that during a solar eclipse by the moon, its mass would slightly curve space, and he could experimentally confirm this with calculations. The second example is the anomalous shift in Mercury's perihelion. Eventually, after developing the special and general theories of relativity, Einstein aimed to create a third one, even more grand. His goal was to unify all known interactions in the universe into a single equation. In 1869, Dmitry Mendeleev dreamed up the idea of organizing all chemical elements. Waking up, he created the periodic table, showing their periodic properties. This table united over 60 known elements, but it had gaps. Mendeleev was able to predict the characteristics of missing elements using this table. But what made the elements group this way? What processes or laws of nature underlay this order? In 1898, Marie and Pierre Curie discovered new unstable elements. One of them, radium, glowed without a visible energy source, challenging the principle of energy conservation. This pointed to the need for a new theory. Previously, scientists believed chemical elements were unchangeable and eternal. However, now in laboratories, scientists observe some elements, like radium, transforming into others while emitting radiation. Scientists measured their decay rate and found that they decayed over thousands and even billions of years. The Curie's discovery shed light on an old dispute. Geologists studying the slow processes of rock formation assumed Earth existed for billions of years. However, Lord Kelvin, a renowned physicist, thought Earth cooled down in just a few million years. So who was right? It turned out geologists were closer to the truth. Lord Kelvin had not considered nuclear interactions. This process could heat Earth's core for billions of years due to the decay of radioactive elements like uranium and thorium. This nuclear interaction became the energy source for earthquakes, volcanoes, and even continental drift. In 1910, Ernest Rutherford conducted an experiment by placing radium in a lead box with a small hole. A thin ray of radiation emerged, which he directed at a gold foil. It was expected that the gold atoms would absorb this radiation. To his surprise, the radiation from radium passed through the foil as if it wasn't there. This was a sensational result. It meant that atoms were mostly empty space. In 1900, Max Planck, a German physicist, explored a simple question: why do hot objects emit light? Blacksmiths for centuries knew that heating objects changed their color from red to yellow and blue. But when physicists tried to calculate this effect, they faced a problem. Newton claimed that atoms vibrate faster when heated. According to Maxwell, vibrating changes emit electromagnetic radiation as light. At low frequencies, the combined model worked, but as frequency increased, the light's energy approached infinity, which was absurd. Planck then suggested that energy is actually emitted in discrete packets, which he called quanta. He found that he could accurately calculate the energy emitted by heated bodies. The hotter the object, the higher its radiation frequency. That's why we now know the sun's temperature is about 6,000 degrees Celsius. After his research, Planck determined the size of these packets of light energy, known as quanta, and described them using a constant. If Planck's constant were zero, quantum theory equations would reduce to Newton's classical equations. Simply put, all of the strange behavior of elementary particles like quantum entanglement, superposition, and quantum tunneling would easily transform into Newton's laws we know by assigning Planck's constant a value of zero. This is why we don't notice quantum phenomena in everyday life. Our perception of the world is based on Newton's macro laws, as Planck's constant is a very, very small value, affecting only the subatomic world. In 1905, Einstein applied quantum theory to light, showing that light is not just a wave, as Maxwell predicted, but also a particle, photon, as Planck predicted. It consists of photons, which are quanta. Each photon creates surrounding electric and magnetic fields. Like waves, they follow Maxwell's equations. But if light exists in two forms, as a particle and as a wave, could electrons also have this strange duality? The answer to this question was destined to shake not only the world of modern physics, but civilization itself. Physicists, to their surprise, found that electrons previously thought of as ordinary particles can also exhibit wave properties. I think you all know about the double-slit experiment explaining the nature of light's interference pattern. Yes, the one that Hugh Everett, David Deutsch and other physicists interpret as us living in a multiverse. Here is an example of a similar phenomenon that my friend photographed: light diffraction. In this case, the sun's rays are entering a room through a narrow slit between the curtains. There are scientific experiments where a photon passes through 3 or more slits, but the classic experiment involves 2 slits. Let's remember what it's about. To demonstrate light interference, you can take 2 sheets of paper and place them in sequence. In the first sheet, make 2 slits and direct a stream of electrons at it. It's best to do this not with a flashlight, but with a laser pointer or even natural sunlight. You would expect 2 stripes to appear on the second sheet, corresponding to where the electrons pass through. But in practice, we see a series of vertical stripes characteristic of wave interference. Electrons passing through a double slit show wave properties, as if they pass through both slits at the same time. Even when sending electrons one by one, interference still occurs. This suggests that a single electron somehow passes through both slits simultaneously. It's astonishing. How can an electron, a separate particle, interact with itself as if it passed through 2 slits at once? Moreover, other experiments have shown that electrons can disappear and then reappear in different places, which is very strange. If Planck's constant affected large-scale objects, our worlds would be incomprehensibly strange, with objects disappearing and reappearing or being in 2 places at once. Quantum theory, though seemingly confusing and full of paradoxes, quickly showed remarkable results. In 1925, Erwin Schrödinger, an Austrian physicist, presented his famous equation accurately reflecting the movement of wave particles. It's so fundamental that the entire periodic table can be explained through this equation. At the age of 22, the young and daring physicist Paul Dirac decided to merge the concepts of space and time, creating a wave equation in line with Einstein's special theory of relativity. He developed a theory with 4-dimensional symmetry, making it attractive and concise. The complex elements of Schrödinger's equation were replaced with a single 4-dimensional equation. Dirac's equation also explained where the magnetic field in magnets comes from, without moving charges. It turned out that electrons have a spinny property called spin. It's the spins of electrons in metal that create the magnetic field. Dirac's equation opened the door to understanding a new form of matter called antimatter. It's identical to regular matter but has the opposite charge. For example, an anti-electron or positron has a positive charge. Theoretically, anti-atoms made of positrons revolving around antiprotons and antineutrons are possible. For instance, atoms of antihydrogen were created in the mid-1990s. However, when matter and antimatter come into contact, they explode, releasing a huge amount of energy. In the context of a universal theory, antimatter is crucial, because every particle should have an antiparticle. Previously, symmetry was seen by physicists as a beautiful detail but not critically important for theories. But now they were amazed by symmetry's ability to predict new and astonishing phenomena like antimatter and electron spin. Physicists realized that symmetry is a fundamental characteristic of the universe. Yet there were still unanswered questions. For instance, if an electron has a wave characteristics, what creates this wave? What exactly is oscillating? And how can a wave pass through two different openings at the same time? Heck, why can't my coffee be in two places at once, but an electron can? The question that came to the forefront divided scientists worldwide into two camps. In 1926, Max Born argued that the true essence of oscillation is the probability of finding an electron in a certain place. Thus, we can't know exactly where an electron is, but we can determine the probability of its presence in a specific location. This approach was a revelation. It implied that the future can't be precisely predicted, only the likelihood of events can be estimated. Despite the success of quantum theory, many criticized it. Einstein noted that the more effective quantum theory becomes, the less logical it seems. Discussions about the philosophical aspects of wave theory continue today. Nobel Prize laureate Richard Feynman remarked, "I think I can safely say that nobody understands quantum mechanics." On one side of this millennium-long debate stood Einstein and Schrödinger. On the other were Niels Bohr and Werner Heisenberg, pioneers of the new quantum concept. The fate of this confrontation was decided at the Sixth Solvay Conference in 1930 in Brussels. It was there that the main debates of the era took place, where the giants of physics faced off in a battle over the meaning of reality itself. Paul Ehrenfest described a moment after one of the debates. "I'll never forget how the two opponents left the university club before my eyes. Einstein was a majestic figure, walking calmly with a faint ironic smile, while Bohr, terribly upset, scurried alongside him. Einstein actively criticized quantum theory, trying to highlight its flaws. However, Bohr confidently refuted each of his remarks. In response to Einstein's statement that God doesn't play dice with the universe, Bohr replied, "Stop telling God what to do." Most historians believe that Bohr, Heisenberg, and other supporters of new quantum theory won this debate. But Einstein managed to expose and highlight the weaknesses of quantum mechanics, pointing to its unstable philosophical foundations. Many of his arguments are still relevant today, and at the center of many of them is a world-famous cat. Schrödinger proposed a thought experiment demonstrating the paradoxes of quantum mechanics. Take a cat and put it in a sealed container with a piece of uranium. When a particle emits from the uranium, a Geiger counter will trigger a mechanism that will probably kill the cat. And the question is the cat alive or dead? Since the phenomenon of uranium decay is determined by quantum laws, the state of the cat should be considered through the lens of quantum mechanics. According to Heisenberg, until the box is opened, the cat is simultaneously in two states, both alive and dead. These two states mix until you look inside the box and establish the cat's actual state. In other words, the act of observation somehow mystically determines reality. For Einstein, such an approach seemed absurd. He often asked his guests provocative questions like, "Does the moon exist only because a mouse looks at it?" Despite all the paradoxes of quantum theory and its incompatibility with everyday views of the world, it had an undeniable advantage. Just think, the predictions of quantum theory have been verified to 11 decimal places, making it the most accurate theory of all time. Even Einstein himself acknowledged that quantum theory contains truth. In 1929, he even nominated Schrödinger and Heisenberg for the Nobel Prize in Physics. And even now, almost 100 years later, scientists haven't reached a consensus regarding Schrödinger's cat problem. Most physicists simply use quantum mechanics as a recipe book that always gives the right answer, without paying much attention to its subtle and profound philosophical implications. The old Copenhagen interpretation by Niels Bohr, where observation causes the collapse of its wave function is rapidly losing relevance because today with nanotechnology we can manipulate individual atoms and conduct similar experiments. Therefore, the many worlds interpretation in which reality splits into two parts, in one of them the cat remains alive, in the other is dead, is becoming more popular. After the successes of quantum theory in the 1930s, physicists decided to approach a new mystery. Why does the sun shine? Since ancient times, the sun has been the subject of worship in various cultures. The Greeks praised Helios, who rode across the sky every day in his shining chariot, illuminating the earth. The Aztecs, Egyptians, and ancient Indians also had their versions of the sun god. Thus, the source of the sun's energy remained a mystery for a long time. At the dawn of the 19th century, Joseph von Fraunhofer created unique spectrographs for his time. Light passing through a prism forms a rainbow on the screen, showing the difference in wavelengths, including dark lines. These lines appear due to quantum jumps of electrons, which either absorb or release energy. Since each chemical element has its unique spectral lines, this allows determining the composition of a substance. Therefore, spectrographs are actively used, for example in forensics for trace analysis. By analyzing the spectral lines of sunlight, scientists discovered that the sun is primarily composed of hydrogen. After Fraunhofer's work, astronomers studying the light of stars concluded that these celestial bodies are made of materials found on Earth. This confirmed that the laws of physics operate the same throughout the universe. Erwin Schrödinger, one of the creators of quantum mechanics, also pondered another eternal question: what is life? Schrödinger believed that quantum mechanics could unlock the secret of the origin of life. For centuries, scientists and philosophers speculated about a special life force that animates matter when something invisible, like a soul, enters it. Many adhere to dualism, believing that the physical body and soul coexist together. However, Schrödinger was convinced that the mystery of life must be encoded in a specific molecule that follows the principles of quantum mechanics. Just as Einstein eliminated ether from physics, Schrödinger wanted to remove the concept of a life force from biology. In 1944, he published the book called What is Life? In this book, he described the principles according to which the code of life is transmitted from generation to generation, not due to some ephemeral entity, the soul, but because of a special molecule contained in cells. Back then, human knowledge in molecular biology was, let's say, like reading tea leaves. However, Schrödinger's book inspired James Watson and Francis Crick to search for the key molecule. Understanding that it was too small to be seen with the naked eye, they used X-ray crystallography, whose wavelengths matched the size of molecules. X-rays passing through crystals of organic substances scattered, forming unique patterns. These patterns helped reveal the atomic structure of the crystal. I think it's amazing. Quantum mechanics is such an advanced tool that it can determine the position of atoms in molecules. Similar to children's construction toys like Lego, atoms can be assembled in the desired order, recreating the structure of complex molecules. Watson and Crick discovered that DNA is the key component of the cell nucleus. Based on X-ray images taken by Rosalind Franklin, they determined that DNA has the shape of a double helix. Thus, the structure of DNA was discovered using quantum mechanics. Remarkable! This result vividly demonstrated that the process of reproduction could be shown at the level of molecules. This breakthrough allowed researchers to start the truly ambitious Human Genome Project, aiming to provide a detailed atomic description of DNA. As Charles Darwin predicted in the 19th century, scientists can now create a genealogical tree of all life on Earth. Einstein failed to create a comprehensive field theory, largely due to a lack of information about nuclear interactions. There are two types of interactions, strong and weak. Considering that protons have a positive charge and theoretically should repel each other, the atomic nucleus should in theory fly apart into pieces. However, it's the nuclear forces that counteract this repulsion and hold the nucleus together. Without these forces, our world would simply crumble, turning into many separate particles. Thanks to the strong nuclear interaction, the nuclei of many elements can maintain their stability throughout the existence of the universe. But there are nuclei that are unstable due to an excess of protons or neutrons. If there are too many protons, electrical forces can break apart the nucleus. If there are too many neutrons, the internal instability can cause decay. Weak nuclear forces can't hold a neutron forever, so over time it disintegrates. This process produces three particles: a proton, an electron, and another particle called an antineutrino. In 1929, Ernest Lawrence invented a cyclotron, which became the basis for modern particle accelerators. The cyclotron works on a simple principle. A magnetic field causes protons to move in a circular trajectory, where they receive an energy boost from an electric field with each turn. After many turns, protons can reach energies of billions of electron volts. Then these protons are aimed and collided with other protons. By analyzing these collisions, scientists have been able to discover previously unknown particles. This process is kinda like trying to determine the properties of a piano by throwing it out of the window and analyzing the sound it makes as it falls. Despite the clumsiness of the method, it's one of the few ways we have to investigate the internal structure of a proton. When scientists first collided protons in an accelerator in the 1950s, they discovered many unexpected particles. This shocked them, as it was expected that the structure of the nucleus would become simpler upon deep analysis, not more complex. These results could lead one to think that nature acts inconsistently. Disappointed by the continuous discovery of new particles, Robert Oppenheimer suggested that the Nobel Prize in Physics should be given to someone who does not discover any new particles for a year. Enrico Fermi joked that if he had known there were so many particles with Greek names, he would have chosen to be a botanist. Physicists were overwhelmed with information about elementary particles. Because of this problem, some thought that the human mind was fundamentally incapable of understanding the world of subatomic particles. They compared it to trying to teach a dog mathematical calculations. However, the situation began to clear up thanks to the work of Murray Gell-Mann, who proposed that a proton and neutron are made up of three smaller particles, named quarks. In 1964, the particle omega-, predicted by his theory, was discovered, earning Gell-Mann the Nobel Prize. Scientific research related to the weak nuclear interaction, which is 1,000,000 times weaker than the strong interaction, continued to develop actively. The weak nuclear interaction cannot hold together some atomic nuclei, leading them to decay into simpler components. This mechanism, known as radioactive decay, explains the high temperature inside the Earth and is the reason for volcanic eruptions and earthquakes. To understand the nature of this interaction, scientists proposed the existence of a new particle. For instance, an unstable neutron eventually decays into a proton and an electron in a process called beta decay. To accurately describe this phenomenon, it was necessary to add another particle to the equation, named neutrino. Neutrinos are called ghost particles. Because they can pass through entire planets and stars without any interaction or absorption. They can move nearly at the speed of light, and their numbers exceed all atoms in the universe. Right now, a stream of neutrinos from deep space is passing through your body, and a part of it has even passed through our planet. These particles could freely pass through a solid lead thickness stretching from Earth to the Sun. Wolfgang Pauli, who predicted the existence of neutrinos in 1930, once lamented, "I have done a terrible thing. I have postulated a particle that cannot be detected." However elusive this particle was, it was eventually experimentally detected in 1956 when analyzing the powerful radiation emitted by a nuclear reactor. In an attempt to better understand the weak nuclear interaction, scientists proposed a new principle of symmetry. Since the electron and neutrino are a pair of weakly interacting particles, it was proposed to unite them. This assumption led to the creation of a new electroweak theory, which combined electromagnetism magnetism and weak nuclear interaction. The electroweak theory, developed by Steven Weinberg, Sheldon Glashow, and Abdus Salam, earned them the Nobel Prize in 1979. Instead of uniting with gravity, as Einstein had speculated, light joined with weak nuclear interaction. Thus, from many uncertainties, a new concept known as the Standard Model of elementary particles began to form. Interestingly, the Standard Model could precisely determine the properties of matter in the past, up to a fraction of a second after the Big Bang. However, despite the detail of the Standard Model and its ability to reflect our understanding of the subatomic world, it had a number of gaps. First and foremost, it lacks gravity, which is a significant omission, considering that gravity controls the macrostructure of the universe. When trying to add gravity to this model, scientists encounter unsolvable equations, making the model unsuitable for explaining some mysteries of the universe, like events before the Big Bang or what's inside the black holes. The Standard Model was created by merging various theories, making it resemble a mosaic of different parts. As one physicist put it, it's like taping together a platypus, an anteater, and a whale with duct tape and declaring the result the most elegant creation of nature. In reality, such a creation could only be loved by its mother. In the Standard Model, there are many unsettled parameters, such as the mass of quarks and the intensity of interactions, with 20 artificially added constants without a clear understanding of their origin and meaning. To understand the scale of the problem, let's just compare Einstein's equation and the Standard Model. Einstein's theory, for example, can be expressed in one short equation, whereas the equations of the Standard Model, in a highly abbreviated form, take up almost a page when written down, as they detail various quarks, electrons, neutrinos, gluons, Young-Mills particles, and Higgs particles. All the physical laws of the universe could in principle be derived from this single page of equations. The problem is that the two theories, Einstein's theory of relativity and the Standard Model, are based on different mathematics, different initial assumptions, and different fields. The ultimate goal is to combine these two sets of equations into a single unified system. Any theory that claims to be a theory of everything must contain both sets of equations, but at the same time remain finite. So far, the only theory capable of this is string theory. At the end of the 19th and beginning of the 20th century, two key concepts dominated science: Newton's laws of gravity and Maxwell's equation for describing light. Einstein realized they were incompatible and was confident that one of them would prove incorrect. The fall of Newtonian mechanics marked the starting point for the greatest discoveries of the 20th century. Today, history is repeating itself. Science again faces two competing concepts. On one hand, there is Einstein's theory of gravity, explaining black holes, the Big Bang, and the expansion of the universe. On the other hand, there is quantum mechanics, studying the world of particles. However, these theories do not fit together. The next breakthrough will likely unite these two directions. In 1968, two scientists, Gabriele Veneziano and Mohiko Suzuki, discovered an interesting formula created by the mathematician Leonhard Euler in the 18th century. This strange formula seemed to describe the scattering of two elementary particles. But how could an abstract formula from the 18th century describe results obtained with modern accelerators? That's not how physics works. Soon, other scientists, including Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind, realized that this formula represented the interaction of two strings. They expanded this idea into an entire army of equations, representing the scattering of multi-strings. After this, they were able to introduce rotating particles into string theory. String theory became like an oil well that unexpectedly gushed a fountain of new equations. But where did so many different particles come from? The theory stated that each vibration of a string, like a musical note, corresponds to a certain particle. Electrons, quarks, and Young-Mills particles are just different harmonies of one vibrating string. What makes this theory unique is its natural inclusion of gravity. In it, the graviton is one of the lowest vibrations of the string. Even if Einstein had never developed his theory of gravity, we would have found it by looking at the lowest vibration of the same string. Here is an example. When analyzing the collision of two graviton particles, the result turns out to be infinite and therefore meaningless. However, in the case of the collision of two strings, the result consists of two components that precisely cancel each other out, helping to create a finite theory of quantum gravity. As the string theory developed, it revealed features that give me goosebumps. Specifically, it turned out that it can only function in 10 dimensions. This was a real surprise for physicists, as such discoveries had never been made before. Usually, theories can be adapted to any number of dimensions. We seem to live in a three-dimensional space, moving left-right, up-down, and forward-backward. Considering time, 4 dimensions are enough to describe any event. For example, to arrange a meeting in Berlin, it's enough to specify an address, floor, and time. Our perception is limited to these 4 dimensions. Imagining additional dimension is almost impossible. That's why the study of multidimensionality in string theory is primarily conducted through mathematics. If the assumptions of string theory are true, then our universe was originally 10-dimensional. However, such a model of the universe would have been unstable, and 6 of the 10 dimensions eventually collapsed, becoming so tiny that atoms are too large to interact with them. Symmetry in equations has long been considered a good but not mandatory quality. But in quantum physics, symmetry becomes a key element. Michio Kaku writes, "Only in recent decades have physicists realized that symmetry is not just a pleasant property of a theory, but rather its central component. The requirement of a theory's symmetry often can drive out divergences and anomalies inherent in asymmetrical theories. Symmetry is a sword with which physicists slay dragons let loose by quantum corrections." Dirac discovered that his equation for the electron indicates the electron's spin, a property similar to rotation familiar to us in everyday life. Later, it was found that all elementary particles have spin, which can be integer or half-integer. Particles with integer spin, such as photons, Young-Mill particles, and gravitons, are called bosons and carry the fundamental interactions of the universe. On the other hand, particles with half-integer spin, including electrons, neutrinos, and quarks, are called fermions. Protons and neutrons, and thus atoms that form our matter, are made from fermions. Bunji Sakita and Jean-Luc Gervais showed that string theory possesses a new type of symmetry, called supersymmetry. Now it's the most comprehensive symmetry ever discovered in physics. It unites all known particles. This symmetry allows for the intercharge of particles in equations without changing the underlying structure. Each particle has its twin in this symmetry, known as a superparticle. For example, the electrons pair is the selectron, and the quarks pair is the squark. Michio Kaku writes, "Something remarkable happens in string theory. When calculating quantum corrections to string theory, we have 2 components. There are quantum corrections coming from fermions, and those coming from bosons. Miraculously, they are equal in magnitude but opposite in sign. One of the terms can be positive, but there is also a negative term. When added together, they cancel each other out, leaving a finite result." For a long time, scientists struggled to unite Einstein's theory of relativity and quantum physics. However, supersymmetry allows neutralizing infinities, simplifying this union. Einstein once compared his theory of gravity to marble, smooth, elegant, polished. In contrast, matter resembled wood, rough, chaotic, and lacking a proper geometric structure. Einstein's ultimate goal was to create a unified theory that would combine marble and wood, meaning a theory entirely made of marble. This was Einstein's dream. String theory in this case combines marble, bosons, and wood, fermions. Steven Weinberg, a Nobel laureate, wrote, Though symmetries are hidden from us, we can sense that they are implicitly present in nature, controlling everything around us. It's the most exciting idea I know. Nature is much simpler than it appears. Nothing gives me more hope that our generation truly holds the key to the universe in our hands, that within our lifetime we can say why everything visible in the vast universe with galaxies and particles is logically inevitable. To summarize everything said in this video, it appears that symmetry very much resembles the key to unifying all the laws of the universe. Let's just list them. Symmetry brings order to chaos, forming ordered systems from chemical elements and particles. It helps to reveal missing links in theories, predicting new elements or particles. Symmetry finds connections between objects that seem independent, between space and time, matter and energy, electricity and magnetism, fermions and bosons. It leads to the discovery of new phenomena, such as antimatter, spin, and quarks. Symmetry eliminates undesirable consequences that could destroy a theory. Quantum corrections with divergences and anomalies are eliminated using symmetry. It changes the original classical theory. Quantum corrections to string theory change the initial theory, determining the dimensionality of spacetime. It is believed that at the beginning of the universe's birth, there was a single superinteraction, whose symmetry included all particles. However, this symmetry began to break down. Gravity emerged first, then nuclear interactions, leaving electromagnetic forces on their own. As a result, the current world appears fragmented, where each interaction differs from the other. The task of physicists is to reunite these broken parts. String theory has the necessary potential, but there is a problem. It can't be expressed through a single equation. In 1995, a significant event led to the emergence of M-theory. The issue was that there were 5 different versions of string theory, differing only in the way they organized spins. This raised questions, as most scientists believed that the universe should be unique. Physicist Edward Witten discovered a hidden 11-dimensional theory named M-theory. At its core are membranes, akin to the surfaces of spheres and donuts. Witten asserted that the 5 different string theories could be interpreted as 5 ways of transforming an 11-dimensional membrane into a 10-dimensional string. In other words, all these versions of string theory are different mathematical models of one M-theory. It follows that string theory and M-theory are different projections of the same idea. But how can one 11-dimensional concept give rise to 5 10-dimensional ones? Imagine a beach ball. If you let out almost all the air, it takes the shape of a sausage. If deflated completely, it becomes a string. Essentially, a string is a deflated membrane. Starting with an 11-dimensional ball, it can be mathematically proven that there are 5 ways to deflate it, turning it into a 10-dimensional string. Or recall the parable of the blind man who first encountered an elephant. One, feeling the ear, decided that the elephant was like a fan. Another, after encountering the tail, decided the elephant was like a rope. A third, having examined a leg, thought the elephant resembled a cylinder. But in reality, looking at the elephant in its entirety, we see it as a 3-dimensional, heavy charmer with kind eyes and velvety ears. Similarly, the 5 string theories are associated with different parts of the elephant, but the true appearance of M-theory, the elephant, remains to be revealed. Just 2 years after presenting M-theory in 1995, Juan Malsedina made a phenomenal discovery. His research showed that the supersymmetric Young-Mills theory, operating in 4 dimensions, is mathematically equivalent to a 10-dimensional string theory. This caused a real stir in the physics world, and by 2015, Malsedina's discovery was referred in 10,000 articles, making it the most influential work in high-energy physics. At the beginning of the video, we discussed the duality in Maxwell's equations between electric and magnetic fields. These equations retain their form if these fields are interchanged. Similarly, there are 5 10-dimensional string theories that are dual to each other, as all of them are united into a single 11-dimensional M-theory. Thus, duality indicates that both theories are different sides of the same phenomenon. Nevertheless, Malsedina proved that there is an additional duality between 10-dimensional strings and the 4-dimensional Young-Mills theory. This finding was surprising, indicating deep connections between gravitational and nuclear interactions in different spatial dimensions. Michio Kaku writes, "Usually, dualities are found between strings of the same dimension. By rearranging the terms describing these strings, for example, we can often replace one string theory with another. This creates a whole web of dualities between different string theories defined in the same dimension. But a duality between two objects defined in different dimensions was unprecedented." The question raised by this duality is not just academic speculation. It affects our understanding of nuclear interaction. For example, we already know that the best way to describe it is through a four-dimensional gauge theory based on the Young-Mills field. However, no one has yet been able to find an exact solution to this theory. Considering that gauge theory can be related to 10-dimensional string theory, this suggests a possible interconnected understanding of quantum gravity and nuclear interaction. This idea has drawn attention to the fact that key characteristics of nuclear interaction, such as the mass of the proton, may be best explained through string theory. This has caused a real crisis of self-identification among physicists. Nuclear physics specialists, traditionally dealing with three-dimensional objects, suddenly found themselves needing to study string theory in 10 dimensions. This raised questions about the connection between gravity and gauge theory. Additionally, an interesting principle called holographic was discovered. A hologram is a two-dimensional image that can reproduce a three-dimensional image with a laser beam. This is similar to how R2-D2 from Star Wars projected the image of Princess Leia, and how ghost houses are created in Disneyland, where three-dimensional ghosts glide around you. Similarly, in black holes, all information about objects inside can be encoded on the two-dimensional surface of the event horizon. If you throw a Bible into a black hole, according to quantum mechanics, the information contained in the book cannot disappear. So where does it go? Probably it is distributed over the surface of the event horizon. Thus, the two-dimensional surface of a black hole contains complete information about all three-dimensional objects that have fallen inside. This discovery challenges our understanding of reality. We consider ourselves three-dimensional beings, but in reality, we might be part of a hologram. Michio Kaku writes, "Perhaps the three-dimensional world we perceive is just a shadow of the real world, which is actually 10 or 11-dimensional. Moving in three spatial dimensions, we perceive the movement of our real selves in 10 or 11 dimensions. As we walk down the street, our shadow follows us and moves like us, except it exists in 2 dimensions. Similarly, we ourselves might be shadows, moving in 3 dimensions, while our true selves move in 10 or 11 dimensions." It turns out that string theory continues to offer more and more amazing conclusions today. This indicates that we still poorly understand the foundations on which it is built. For this reason, the experimental verification of string theory seems premature. Once we uncover its true principles, we may find a way to its experimental verification. Then we can definitely say whether string theory is the theory of everything or the theory of nothing. Thank you for watching, guys! In a couple of weeks I will post the next video on the channel and tell you more about string theory. Meanwhile, please subscribe to the channel to get notifications of new videos and check out my Patreon, where I have posted the selection of books on the theory of everything.